Hello everyone and welcome to RTFI Pro. My name is George Jakes and today we will be presenting the first of a series of videos on X-ray tubes. The first video today we will be discussing the primary parts of the X-ray tube and how it produces X-rays. So let's look at the X-ray tube main components. The tube has three primary parts, which are the cathode, the anode, and the tube housing. Let's now review these parts separately to provide a description on what the purpose and function are for these parts. The cathode. The cathode is negatively charged and is used to create the electrons, which are accelerated to the anode, which is positively charged. Hence, the negative electrons becomes attracted to the positive anode. But how does this occur? Well, let's look deeper into the cathode. The cathode consists of two main parts, the filament and the focusing cup. Within the cathode, there's a thin tungsten wire filament, which when a high amperage current is applied to the filament becomes heated in a process of thermionic emission. So what is thermionic emission? Thermionic emission is basically the emission of electrons from a heated source. This filament is typically 1 centimeter or less in length and about 2 millimeters in diameter. Some X-ray tubes have two filaments, known as a dual focus X-ray tube, which one filament is 1 centimeter or less in length and the other is 2 centimeters or less. The purpose of a dual focus X-ray tube would be to be more diversified for examination, as it can be used for both lower and higher MA for thinner and thicker objects. The smaller filament would be used for the examination of smaller parts, as it can only withstand small MA, as higher MA will cause it to burn out and break. The larger filament would be used for thicker parts and higher MA, as it would be able to withstand the higher heat. Now let's look more into thermionic emission. When the filament is heated by a current, it creates a cloud of electrons, which is called space charge, namely due to the electrons being out in space. As the MA is increased, the number of electrons increases, and the opposite occurs when the MA decreases, as fewer electrons are emitted to the anode. However, there is a limit on the maximum number of electrons produced from increasing MA, which is estimated to be about 1,000 MA. At this level, no more electrons are produced, and this is known as the space charge effect. Now we have the focusing cup, which is something like a barrel to a gun. For instance, we need to repel and focus the electrons into a narrow path towards the tungsten target, and this is done with the focusing cup. Without the focusing cup, the electrons would repel out in space in different directions. So what do we know about the focusing cup? It is negatively charged, typically made of copper or molybdenum, concave shaped. Primary purpose is to condense the electrons into a small beam towards the anode. As we previously discussed the small and large filaments, the smaller the filament creates a narrow aligned X-ray beam, resulting in greater spatial resolution, sensitivity, and definition of the radiograph. The larger the filament will withstand more heat, but in turn will result in a poorer aligned X-ray beam with decreased spatial resolution, definition, and sensitivity, but benefits in the use for larger objects and thicknesses. In summary, the importance of the electron beam is spatial resolution. As the narrower and tighter the beam, the greater spatial resolution and quality radiograph, and the opposite occurs when the electron beam is larger. The second major component of the tube is the anode. The anode is positively charged and made of tungsten, which absorbs the electrons and creates X-rays. The anode is typically at an angle around 20 degrees. Tungsten is used because of its high atomic number, its high melting point, high thermal conductivity, and low vapor pressure. In addition, the anode is attached to a copper stem, which is a good conductor of heat, as heat is impacted at the target. It is being dissipated efficiently from the tungsten anode and copper stem to prevent burnout of the machine. There are two types of anodes, a stationary anode and a rotating anode. Stationary anodes is designed for lower MA as they cannot withstand higher heat when higher MA is used. Rotating anodes are used in its place when higher MA is used because the anode rotates and the heat ends up being dispersed over sections of the rotating anode instead of one area as in the stationary anode. The focal spot. The focal spot is the area on the target of the anode that is approximately 1 millimeter by 3 millimeters. This is the area that the electrons collide on the anode target. The focal spot needs to be large enough to absorb the heat, but in turn small enough to provide greater sharpness on a radiograph. The focal spot is angled about 20 degrees to reduce the heat and to create a smaller effective focal spot, which can typically be 1 millimeter by 1 millimeter, which provides greater sharpness or definition of a radiograph. X-ray production. X-ray photons are produced from the focal spot after the sudden stop of the electrons traveling from the negative filament of the cathode. The electron speed can be controlled by the voltage, as increasing the voltage increases the voltage difference across the X-ray tube. By increasing the kilovoltage, we can create faster electrons, and decreasing the kV, we can create slower electrons. As mentioned previously, the quantity of electrons can be controlled by increasing or decreasing the MA. Therefore, this determines the number of electrons traveling to the anode. When electrons travel to the anode, they result in a sudden stoppage with the interaction of the atoms of the tungsten target. This atom interaction will create energy in the form of X-rays that consist of both a diverging beam and a central beam. Glass filter. Both the anode and the cathode are surrounded by the glass envelope, which purpose is to create an air-free vacuum around the tube, which purpose is to prevent oxidation and corrosion. The complete glass housing is enclosed with an insulating oil or other cooling method, which is used to reduce the heat. Tube housing. The final major component of the tube is the tube housing, also known as metal or lead housing, which serves as a shield to prevent the X-rays from being emitted throughout different areas of the tube. The tube housing absorbs all the X-ray photons except the ones aimed at the object being examined. So now let's give a quick review to summarize how X-rays are produced. We have learned that first we will require a negative cathode, which contains a negative filament that will be required to be heated by current, and this will cause the emission of electrons which are attracted to the positive anode. The electrons interact with the atoms of the tungsten target after the sudden deceleration or stoppage at the target, which results in the production of energy in the form of X-rays. Well folks, this concludes our topic for this week. If you like this video, give it a thumbs up and subscribe to our channel. Stay tuned for more videos on X-ray tubes. Until next time, work safe and expand your knowledge for an increased reliability of inspection.